Thank you very much. It's a real honor to be here. So today I'm going to be speaking about autonomous robotic ocean observing systems. I'm a professor at robotics and control at Oslo Metropolitan University. This is a relatively new university in Norway, but it's the third largest in the amount of students. And we are located in the center of Oslo. It's a very urban university, and we do a lot of activity related to our local region. And I'm a member of the Oslo Met Artificial Intelligence Lab. We have several research and industry collaborations in this area. It's very important for us. And as Tom mentioned, we recently opened Ocean Laboratory. It's the Oslo Met Ocean Lab. It's a facility which is located a few meters from the fjord in the center of Oslo. And it's very special because it's a combination. We are not aware of similar small laboratories. It's not very big in size, but it's very special because it's a combination of, on the first floor, we have a makerspace. That's a place where students and other visitors can learn to do prototypes, electronics, CNC, learn to use different softwares. And then in the second floor, we are focused on research activities. So we have office space for professors, for PhDs, for postdocs. And then in the third floor is themed around innovation. So there, in the third floor, we have a place for startups and for students and employees that want to convert their ideas related to the ocean, technology, and sustainability into businesses. Right. So, this what I take it. Yeah. So, blue economy. I'm gonna focus on the part of the definition we saw previously today that talks about the fact that we need to create business, jobs, and activity and economic activity while preserving the ocean's health and ecosystems. And this is not an easy task. It's very challenging. And there are several reasons for that. One was briefly mentioned today in a previous presentation, is the fact that Wi-Fi doesn't work underwater. It's very difficult to communicate. GPS signals do not work underwater. The distances are enormous, are vast, so it's very difficult to really reach to very remote areas. So there are a lot of challenges, not to mention the depths and the mechanical challenges for designing equipment that can withstand such depths. I'm going to make an overview of some of the robotic technologies that have been used in the last years. One very popular is remotely operated underwater vehicles, ROVs. They have an umbilical, a cable, so they somehow require some support vessel to be on the vicinity. So they don't have a large range unless a ship or a vessel follows up. Another type is autonomous underwater vehicles, AUVs. Norway is manufacturer of Kongsberg Maritime manufactures these AUVs, Hugin from Kongsberg Maritime, one of the most advanced in the world. These kind of vehicles, they don't have an umbilical, so it means they can swim freely. This makes that they can be very stable platform to collect data. So for instance, if you are worried about having collecting information about the seabed, doing a bathymetric map, or mapping a pipeline or an underwater cable. These are the type of platforms that produce the most high quality data. And it is very interesting because this autonomy topic that was mentioned on a previous presentation, this has been from day zero a very big challenge in autonomous underwater vehicles, because once they dive, you don't have a possibility to transmit video. They have to be somehow take decisions on their own. So autonomy has been on the agenda for a long time in the marine robotics community. In the recent years, there has been an emergence of new robotic platforms that allow to be operated over a longer distance by using energy from the environment. One good example, successful example, is the American company Sail Drone. And they have received a lot of investment, and they are, I believe, over 100 of units operating now. Another example is a Norwegian company, Sail Buoy. They have a smaller version of, this is called an unmanned surface vessel. And these are, even though they are relatively small, they have been crossing the Atlantic autonomously. Another successful example is a wave glider. It's also an American company, Liquid Robotics. This vehicle is very interesting because it uses the waves to convert the vertical motion into forward motion. So it's very energy efficient. Then it carries solar panels to power the sensors. So they can be at sea for 3-4 months, which makes it a very interesting platform for ocean observation. Another example, not so known, but very promising also, is the Autonaut. This is a UK company, and also use the energy of the waves to produce forward motion, so there's no propellers. And our good collaborator, NTNU University in Trondheim, they have purchased one unit, and they are working on making it autonomous and use it for diverse marine research projects. This is, we also at the Ocean Lab, we have also a small unmanned surface vessel. This one is battery powered, it has an autonomy of 20 hours, so it's not a long range vehicle, but it's a good platform for us and for our students to test concepts related to autonomy, autonomous ships, obstacle avoidance, and things like that. This is a picture of the center of Oslo. This is some tests a few days ago. So you can see the Opera, beautiful center of Oslo. And this is very near where we have the laboratory. Now, I'm going to talk about another type of vehicle that is very interesting and that I have taken a special interest myself. That is underwater gliders. These kind of vehicles, they don't have a propeller. What they do is they can modify their buoyancy, so they can control if they sink or they float, and they use this to advance, to have a forward motion. So in a very energy effective way, they can travel for long distances. So some of these vehicles have traveled also the Atlantic Ocean. They can be operating for several months, and when they surface, they can communicate via satellite and transmit relevant sensor data. And the future is bright. There's a lot of ideas, a lot of new companies coming with new concepts that can revolutionize the way we gather data from the ocean. One good example is Ocean Infinity with their Armada fleet concept. It's a concept to operate remotely operated vehicles using unmanned surface vessels. So you can make completely autonomous unmanned operations. Another example is a company I'm working with. I'm a co-founder. UC Technologies. So we are developing a concept also for the operation of autonomous underwater vehicles using unmanned surface vessels. This picture also says, I like to show this picture because it shows a very real challenge. I've been describing robotic platforms as a solution because they make obtaining data much simpler, much cost effective, less risk. But there's a very big paradox, challenge nowadays, and that is that to operate those robotic systems, very often we need still manned and big vessels with crews. So this is a very good example. You see a small robot, and to operate this robot, you need a big research vessel with a big crew, still dangerous, harsh environment. This is an example of the Argo Floats. As of 2 days ago, there were 3,863 floats operating on the world. This is one of the most successful international collaborations for ocean science. These floats are small robots, but they can drift in the water column, and every time they surface, they can transmit data like temperature, salinity. So this is very successful, and when you look at this picture, you might think, oh, so many data we have. But if you zoom in a little bit and you realize how large is the ocean, if you just zoom around the Nordic and Baltic areas, we have ridiculously low amount of data points. It's really shocking to visualize how little we measure. So to try to solve this, at Oslo Met, we are coordinating a EU research project. It's called Oasis. And we wanted to demonstrate a system that could fully autonomously deploy and recover small robots so that we can scale up in a way that it's not possible with today's systems and really make the numbers of the data really to the sky. Because that's what we really need. We need a lot of data. So we have a system of miniature underwater gliders. This is a very, very early concept prototype. This is just a thing that goes up and down, that it can be deployed and recovered using drones. These are some swimming pool tests, a very preliminary prototype also, in February 2020, when we were testing one early prototype. And these are some experiments. We are working on concepts, how to make this deployment and recovery fully automated. We are developing the electronics, the mechanical parts, also the control software, the communications. So it's really interesting for students and for researchers because you need to cover a lot of ICT interesting areas to develop these sort of technologies. This is an example of the roll and pitch mechanism. This is the mechanism that allows these robots to change the roll and pitch so they can control, you can control where you go. And these are examples of what sensors we have now. We are measuring depth, of course. We are measuring conductivity, temperature, and we have a fluorimeter that is can use to measure chlorophyll or oil in the water or other different parameters. These are the current prototype that we are assembling as we speak, and we expect to test in the Oslo fjord in 1 month and a half. We are developing also a software or data platform to visualize the scientific data coming from the gliders, as well as to be able to control them. And something that I would like to mention today also, there's a big challenge also on integrating different amounts, different data from different sources. This is a big challenge nowadays. So one thing we need to work is on how to make this data integrated with other existing databases so that researchers and public authorities and the general public can use this data in real time. One other challenge we are working is that of navigating, that is to determine the position of these robots while they are underwater. And we have a big challenge because as we are trying to reduce the cost dramatically to be able to scale up, we need to cut the cost down of every individual unit. We cannot afford to carry some very expensive navigation sensors that the larger autonomous underwater vehicles can carry. So we have to rely on really relatively inexpensive navigation sensors, and we are using machine learning to exploit to the maximum these sensors and be able to obtain relatively acceptable navigation results with an affordable navigation sensor. And this was a paper was presented yesterday by a student of mine in a conference in San Diego. So for timeline, we plan to make some tests in 1 month and a half in Oslo fjord. And by summer next year, we will have the final sea trials of this research project, and we plan to operate 5 to 10 units and to demonstrate the cooperation and the swarming capabilities, how they can communicate with each other. Yeah. And things you can do when you have several units communicating with each other is, for instance, they can help each other to locate sources of contaminants in a much more effective way. They can also be used, for instance, for the understanding of some marine life species. This is one project I was involved, and this was using autonomous underwater robots to listen to Norwegian lobsters that were tracked. They were tracked with an acoustic tracker. So they emit a signal, very weak signal. So if you get close enough with the robot, you can listen and then you can localize where these lobsters are moving and understand their behavior. And one very good property of these gliders, underwater gliders, is that they don't make sound. They can be very silent because when they change the buoyancy and they dive, then there's zero movement. There are no motors, no propellers. So this makes it a very interesting platform for listening to sea life in general. So one of our dreams would be to have the closed loop of an ocean observing system. So you have robots, sensor platforms to collect data. This data is then fed up into database that runs physical oceanographic models or other sort of information that you're interested in obtaining. And then from these models, you generate trajectories and you tell these robots where they need to go in order to optimize the quality of the information. So this is what is called adaptive ocean sampling. And one of our dreams also is to demonstrate this in a vicinity of our ocean lab. So we would like to instrument Oslo Fjord with sensors on the seabed, with drones, with autonomous underwater vehicles, to be able to really see what's going on underwater. I think we have very common challenges in Oslo Fjord as in the Baltic Sea. There are very similarities, I think, from the environmental perspective. So yeah, this is one of our dreams. Thank you very much.